Hello, everyone. Good morning, good afternoon, good evening, depending on the part of the world you are joining us from. Thank you for your interest to join us at our 46th meetup of Kaggle Days Meetup Delhi NCR. And thanks for your support to help the community grow. Today, we are really happy to bring Souradip Chakraborty back on the stage of Kaggle Days Meetup Delhi NCR. I remember we hosted Souradip back in 2020 when the COVID pandemic just hit, and he has delivered a great session back then. And it's truly our pleasure to get him back on our platform to again talk about a very, very interesting topic, that's reinforcement learning from human feedback, the success behind the trending topic or the trending technology of today's world, ChatGPT. So, hello, Shoratip. How are you doing?
Thanks a lot for the invitation for inviting me for this talk. It's a really nice thing to talk again in this forum.
Mhm. Yes, you may start presenting. Thank you.
Okay, sure. So I'll start the presentation. So, is it visible? Is it visible? The screen? Hello? Is the screen visible? Visible. Okay, cool. so so today's topic is reinforcement learning from human feedback, and I'll emphasize a little more on reward design and alignment. And just to introduce myself, I am Shorodip. I'm currently a PhD student at the University of Maryland. And last time when I was here, I was working at Walmart Labs as a research scientist, and then I joined the PhD, and now I'm working as a PhD student. So I think everybody already knows that RLHF, or reinforcement learning for human feedback, has been a major contribution or a major factor in the success of ChatGPT. And I will not start with just the standard way of defining how there is a transformer model, and how uh, directly RLHF has been applied. Rather, I'll try to explain more from a reinforcement learning perspective, and what is reinforcement learning, and why, first of all, why reinforcement learning from human feedback is even needed. What is the motivation of reinforcement learning from human feedback? And then I'll slowly go towards RLHF, and based on the time, we'll see how much of the topics we can cover. So, just for the people who are new to RL and who want to learn RL, I'll just give a brief introduction for reinforcement learning. So, the framework of reinforcement learning is that there is an agent and there is an environment in which the agent is operating. So, whenever the agent is always in a particular state, let's say, and then it takes an action, and the environment, actually, because of the environment, it transits to a next state, and also the environment gives it a reward. So this is the entire pipeline or the framework of reinforcement learning you can think of. So what happens is, let's say you are in this position in this maze, and and this is your goal, right? And you need to iteratively plan how do you reach your goal. So and you are doing this entire process through the reinforcement learning framework. So so this is the path that you eventually plan, that using a sequence of actions that you plan using your policy. Now there is a big problem in reinforcement learning, which is the exploration and exploitation dilemma. So what is this? That you want to exploit the usual place, or do you want to explore some new place? You want to go to some new place where you can get some more rewards, and eventually you learn more about the state. So let's see that how do we mathematically formalize this setup. So this reinforcement learning is typically modeled with a Markov decision process, which is characterized like which is typically denoted by MDP. And what are its component? It has a state space, it has an action space, a transition dynamics, the reward function, and a discount factor. So these are the factors that I just explained. What are these different components? So the main part of objective of a reinforcement learning agent is eventually to learn a policy. What is a policy? A policy is nothing but a parameterization of a function which is like denoted by pi theta, and you have to predict the probability of an action A given the state S. So so you can just simply think this as a neural network which takes the state as an input, and just this is the neural network parameter theta, and it predicts the action to next action to take. and and whenever we have some, we need to learn a parameter, we need an objective, right? So what is this objective? The objective is the maximizing the value function. What is the value function? The value function is nothing but the discounted sum of long-term rewards. So what does it mean? It means that you are not only prioritizing on your current reward, but you need to learn a policy which can actually give you long-term returns. So like, for example, just think of a simple, in this navigation setting, think of a simple thing that you cannot see, you are blinded, let's say, okay, and you want to learn a path to reach to the goal. So what do? You slowly go and you learn from your mistakes, right? And then based on these paths, you eventually grade every state in your mind, that how close is it to the goal, and accordingly you assign every weightage to those states, and accordingly you travel. But the interesting part is that you do not, if there is some state, let's say you see that immediately one state is good, okay, but eventually it might lead to somewhere in a big hole where you might fall down. So naturally you will avoid those states. So those states might be giving you high short term reward, but it will give you very low long term reward. So eventually you want to reach the goal, you want to serve your long term reward, right? So that is the intuition of the value function that you want to maximize, and you want to learn the parameterization. And the most simplest way to do is uh, a stochastic gradient descent, right? So we know that whenever we need to solve an objective, we just apply SGD and we converge. So in this case, instead of SGD, it's a policy gradient. So there are little complexities into that, because there is a Markovian thing going on. So there are some complexities, but eventually you can just think that you take gradient with respect to this loss function, and then you do the policy gradient, which is basically a equivalent to a stochastic gradient ascent step. But if you think carefully, that in this entire framework that I discussed, what is the part or what is the component that is not explicit to the environment? So the component or part that is not explicit to the environment is the reward, right? Right. Basically, like you can think that when the agent is in a particular state, it has it is in a particular state. When it takes an action, let's say go forward, it will go to the next state, right? Because of the dynamics of the environment. So if the environment is simple environment, if you just go right, you will go right because of Newton's law, right? But if the even if the environment has some, let's say, some slippery thing or some friction, you will go to some position which is fixed. That might be stochastic, but that is an inherent component of the environment. But when you reach right, how much reward to give, right? How much you will weight that state, or how much reward you will give, it is not fixed. that is not explicit to the environment, it is implicit. So let me try to give you some example that if you put different type of rewards, the performance can be different, very different indeed. So let's see. So we compare dense versus sparse reward. So what does it mean? So ideally I know that, okay, when the agent is starting from here and when it reaches the goal, it will eventually converge, right? It will go and it will reach the goal. But how do I give the reward? I can give the reward very densely, that every state I give a reward, or I can give a very sparse reward, that whenever it reaches this state, then only I'll give the reward. Right? Clear? So is there any questions till now?
Yes. Shoradip, there was one question which I
Hmm.
think you are covering now. So one of
Hmm.
the community member has asked that can you discuss the concept of the reward signal in reinforcement learning?
Correct.
How does the design of the reward function impact the learning process and the behavior of the agent? I think you are trying to cover it in this slide.
Exactly, exactly. So I'll just
Okay.
cover it in the next 1 to 2 minutes. Yeah.
Sure, sure.
Thanks. Thanks.
Okay.
I'll just have a little water and come one second.
Sure, no worries.
Yeah. Yeah. Okay. So now, so that's a very good question, and it's a very natural question, that how do reward design come into the picture? How do we design the reward function? But so just to understand this concept of reward in reinforcement learning, let's try to see. So now you know that you are in this position and you have to reach this goal, right? And you can give a reward practically of two types, and you can vary in between those two types. Okay, so what is the two types? First is you give a very sparse reward, that okay, I will not give a reward at individual state and actions. I just give a reward when the agent reaches the goal, right? It's like you are playing a chess, and you do not tell your partner, or you do not know that if each of your move is good or bad. You just know at the end of the game. So similarly, here only when you reach the goal, you know that it is good or bad, right? So that is a very sparse reward. And a dense reward is what? That whenever you are at any state, you give a signal, that how close you are to the goal, right? So that is a very good signal to get a gradient, and you can easily learn them, right? So let's see what happens now. Now think from a designer's perspective, right? That let's say you are a designer and you want to design a reward function. So from a designer's perspective, designing a dense reward is very difficult, right? Because at every state and action you have to give some reward. Now for this particular maze it might seem easy. Okay, I can just annotate for this 4 5 actions. But just think, when there are millions of states, then it is almost impossible to give you state and actions, like reward for each state and action, right? But rather, when the rewards are very sparse, it is easy, right? You can just say that, okay, I will give a reward when the robot uh, performs the task, right? And else everything is zero. Whenever it reaches, then and the robot slowly iteratively learns. So what I just explained, it is shown here, that if you see it, if the dead reward is dense, every state and action has some weightage, and if it is sparse, it has just a weightage here, or the reward is here. Now, as I was saying, that these sparse rewards are very efficient for designers to give, and in many cases the rewards are sparse indeed. But if you see that if these rewards are sparse, it is hard to explore, and this relates to the concept that I mentioned at the beginning, which is of exploration, exploitation, challenge, and reinforcement learning. So, and this is and we have tried all these things in the context of real robots and different navigation tasks and various robotics tasks, and we have seen this same thing holds, the same case holds. So why this is happening, why the if impact of reward is so important, is because that when we make the rewards very sparse, you can see that this curvature, or the loss landscape, or the reward landscape, becomes very pointy, right? Ideally, for gradient descent to work nicely, what we want is it should be very smooth, right? So if somebody knows that how we do all the proofs, there are a lot of smoothness assumptions and all. But if the surface is very pointy, like for example, how do we define pointy? You can just think that you have those kind of curvatures where you put a hand or a finger, it will hurt you, right? So when you think like that, it is exactly in that way. So if it is that, naturally gradient descent algorithm or this typical descent ascent algorithms won't do well, right? And that is clear. And also additionally, you can see that as the sparsity of the environment increases or the reward structure becomes more and more and more sparse, the performance of the algorithm worsens. Okay, and this y-axis is regret. Okay, so that is lower the better. So don't get confused and think that it is reward. It's regret. So it is like v use your value function under your current policy. So it is like v pi star minus v pi, right? So it's lower the better. Okay, so now, so one thing is for sure that as we make the rewards more and more sparse, it becomes hard to explore for the agent, and eventually the performance degrades for any algorithm, unless those algorithms are intrinsically motivated or something, right? So now what we understand is that, okay, dense reward is difficult to solve, difficult to design, and sparse reward too is hard to solve. So then what to do, right? Should we leave? Or so then we come to the point that, okay, so we need to design the reward. We need to learn the reward function. We need to do some way that we learn the reward function and the agent can learn under that reward function, and then it will work out, something will happen. And still it is reasonable that we need to design the reward function. It is, and what are the different ways of designing the reward function, right? So one way is demonstration. Uh, what does it mean by demonstration? It's like the human is providing the entire trajectory, right? Like for example, the agent is here and this is the goal, and the human actually provides this kind of a trajectory, right? That it reaches from point A to point B. So the human provides multiple such optimal trajectories, and the and different type of methods are there. Like for example, you behaviorally clone that thing, or you try to do inverse reinforcement learning to learn that and also try to do something better. The next step is learning from human preferences, okay, and feedback. So this is the part where we are more interested in, and from where RLHF and alignment comes into picture. And the third is domain knowledge, right? So there are many scenarios where there are domain experts, and so they practically give you some feedbacks, they give you insights based on which the reward is designed. But for today's session, we are most interested to understand what is RLHF and what is the alignment perspective of it. How does it mean to be, what is the purpose of alignment, right? And what is RLHF? So we'll be focusing on this part. So this is the broader framework that we will be talking about, and this is how reinforcement learning from like reward design, alignment, or RLHF, the entire framework is happening. So it practically happens in three states. And I just want to apologize one thing, that I need to mention a lot of references which I have not yet mentioned, but when I'll be sharing the slide, I will mention all the references. So this is coming from OpenAI's uh, popular paper and slides. So what you do is, the first step is you collect feedback or human feedback, and then you train a reward model, and then you train a policy with reinforcement learning, right? This is the overall pipeline. Now before going into the details of this pipeline, let us take a step back. Okay, so now I have told you about reinforcement learning, what is a policy, and about an agent who is trying to learn the policy. But how does language model come into picture, right? And what is a language model? So I think a lot of people are now already familiar with what is a language model. But what is language model in this context? It is just an reinforcement learning policy, right? It's nothing but just a policy. Like when I showed the first slide, if you remember, there was a pi theta a given x, right? And the language model is just that. So now what is a language model and how the language model has evolved, right? So we know that language model has evolved from starting from TF-IDF if I have to say, it is like there was term frequency, inverse document frequency, then there was word to vec, then there was LSTM based representation learning, and then from there it was self attention, and then from there transformers came, right? That is how it has evolved, and then it has been a beautiful journey till then. So I think you guys already know about what are the foundation models and how it works, but just to give a very very brief introduction, and this is of course from the JLMS slide, we I think you all know. So it's like, how do it encodes? It takes each word and projects it into a QKV vector, which is query key vector. Now it takes the query of word one, and it takes the key of all the other words, finds a cosine similarity. Now and then it gets a score, and then it average the value with those weighted scores. So then that becomes the representation of this word thinking. Similarly, it does for all the word, and then it gets a vector, right, for each word, and then it gets a matrix for the entire context. And then eventually there are a lot of layers and etc. But the overall idea is this. And this attention mechanism has been like proven to be fundamental in the concept of language, and it has been used drastically. And this is the typical architecture, and this is BERT, which was very famous. And very interestingly, it is important to note that language model has been there from 2000. This kind of language models have been there from 2019 or 20, right? um, but still there was not that it was successful, that was used in information retrieval, it was used in classification, and a lot of, let's say, entity recognition, sequence to sequence translation. But this kind of a fundamental breakthrough did not happen, and we assume that the fundamental breakthrough is practically due to reinforcement learning and the human feedback part of. Now what I was saying is, if you see here that there has been different models that are being shown and their performance which are being shown, and it is clear that the performance with RLHF, which is with this PPO, which is proximal policy optimization, or RLHF, is significantly better than supervised fine tuning or the the base language untrained language model also. So that is the point, right? That this RLHF concept that brought a significant uh, impact and a significant performance improvement of the typical foundation language models which have been there from 2019 onwards. So let's try to just little bit go inside it and see that if there is some what are the components of it. So meanwhile, is there any other question now?
Yes, sure. There is one question
Hmm.
which I would say majorly goes into the component of
Hmm.
challenges which might arise. Like I will read up the full question.
Hmm.
It's
Sure,
like,
sure.
could you explain how reinforcement learning is used to fine-tune pre-trained
Hmm.
language models like GPT-3? What specific challenges arise when
Hmm.
adapting these models to generate desired text outputs?
Sure,
So it's
sure.
majorly into the
Hmm.
challenges which might come when we are trying to
Hmm.
include all these components together.
Hmm. 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 Perfect, perfect. Yeah, I think that is correct. So I think that based I'll be answering this question over, like, I think over the period also. And so what is basically what so but the main question is that how do we design the language model policy with human feedback, and how do we make it work? And then second is, what are the challenges in that? And practically
Correct.
that is what I will be discussing in the next few slides. Okay.
Okay.
Now, but at least interestingly, one thing that I think the audience is understanding, and also I think it is understood that uh, that that in this case, in the context of RLHF, the language model is a policy. So that is the first thing that we want to get. Okay. So let me go to the slides, and I think it will be clear eventually what is the question. Okay.
Sure.
Cool. So now this is again, we come back to this RLHF slide, and what we see is there are three steps. We collect demonstration data, train a policy, but main thing is we collect human data, then we collect a pairwise data or a comparison comparison data from the human, and then we optimize the policy, right? So the terminologies are a little bit different from here and there, but overall it means that first you generate lot of data from your language model policy, then you give the policy to the to those generated data to the human ranker, and that human labeler or ranker ranks those policy. Then you learn a reward function from it, and then you train a policy reinforcement learning with a reward. So it is important to note that to train a reinforcement learning, we need a reward function, right? Without that, we cannot learn. And prior to that step is for getting the reward function, we need human preferences, because that is our alignment objective, right? So now what are the phases involved in it, right? So the first phase, that is that reward modeling phase. So basically what we do is we have some prompts, right? We collect some prompts, then we pass those prompts to my language model, and I collect many samples. Like basically I generate a lot of samples, then I take two summaries from there and just give to the human labeler. So the human actually judges that which is better, this one is better or this is better, and accordingly we learn the reward function. So these slides are again, like these parts are taken from like one of the blogs in Weights and Biases by Ayush. So you can have, that is also a nice blog. Now let's go that, okay, so for once the process is clear, let's see that what is the exact loss function to be used. So we use a ranking loss, which is from the Bradley Terry choice model. It's a very old uh, preference based model, and it's still being used, and that's the beauty of I would say this kind of frameworks. So what we do is, so let's say now y1 represent your summary 1 and y2 represent your summary 2, and x is your prompt. So what it does is it's just saying that we learn a reward function r. So it is denoted by the true reward r star, but actually we will parameterize this and learn that. So what it is saying that it learns that. So now we know that the human has preferred y1 over y2. So what it learns a parameter such that this thing, that exponentiating this value divided by sum of exponentiation, this is high, right? So basically it will learn that, okay, for a given x, this y1, so reward function of this x and y1 should be higher than reward function of x and y2. So this is what it is learned. So it is very similar to learning this thing. So if you can learn this parameterization, then it will give you high value for this probability, right? And what it means is, so this is what I was saying, that this is the prompt, this is the summary, this is the not preferred summary. And what it means is, now once you get this probability or of y1 greater than y2, then it just becomes a supervised learning problem, right? Then it is just an regression or a basically classification type of problem, right? So what it means is, in classification, what you know, right, that okay, this data point has this label, right? You know that, and you compute the probability of the label. So if you know the probability of the particular data point, then it is just that it is the log likely or likelihood maximization, right? So pi to the power yi, you can just do that and you can maximize that. So it's just same, it's exactly same. So this part is the reward learning phase, right? Okay. And now comes the RL fine tuning phase. So now once we have this R5, so you understand, right, that from this loss, we can learn this R5. We learn the reward function. Now, once we have this R5, what we do is we need to learn a policy, right? Now, and also always remember that in this context, the policy is basically the reinforcement learning policy, right? So that we should not forget. So now this pi ref. So what is this pi ref? Let's say pi ref can be represented as the supervised like the policy after the supervised fine tuning step, or the untrained or unfine tuned language model. So this is kind of, you can see that the transformer model that you have after the huge massive pre-training, right? Let's say a BERT model. I think BERT model might not be, so there should be something which has a decoder also, right? So let's say that. Now, what we do is we need to learn this parameter theta, right? We need to learn this parameterization policy. So this is the reward function that we have just learned through the preferences using the supervised loss. This is my reference policy. Now, what this tells is, this is exactly a reinforcement learning objective where you need to learn a policy. which I had shown during your value function, right? So this is also, you can think it in terms of a long-term value function. So this is your policy that you need to learn, but you need the scale divergence loss makes you closer, or it keeps you closer to the uh, policy. So it's not like that you are learning something very new, you want to keep closer to the original policy. And beta actually controls this coefficient. So you can just think that I draw a circle around my pi theta of radius 1 by beta, and that beta will control actually that how much I want to move or something. So now this is what the RLHF framework is, and this is done, right? This has been implemented by OpenAI. It collected humongous amount of human labelers. They give ranking. It trained the model, and we know how the performance of ChatGPT is. But there is a challenge, right? Now out of all the challenges, so there are a lot of challenges. The challenges are that this is a sparse reward problem. There are exploration issues, and how PPO is dealing with them. Then there is like how online, like this is happening in an online framework. Like we should collect data. So the first question that comes is, how do we collect this kind of data, right? How do we do this in an iterative way? What is the framework? So this is a summary from one of my recent papers, very recent papers. I'll show the reference at the end. That how can we make this framework online, and how do in an iterative way we can collect this entire data and also learn, etc. So what is happening is, you start with an initial reward function r naught. So given that reward function, you first learn a policy, which is a function of reward function r naught. Then using that policy, you generate a lot of trajectories. So just see this maze, this diagram. So using this current policy, you generate a lot of trajectories. Now the human evaluator evaluates that, okay, how is the trajectories, is it good, bad, or what kind of. So now how is the evaluation done in the context of RLHF? It's like you take two trajectories, you see the preferences, you see the ranking, and you rank them, and based on that you learn a reward function, right? But it is very important to note that the reward function is learned, it is actually a function of the trajectories generated. So you cannot say that this reward function is the best reward function or the ground truth reward function, because it is a function of this trajectories. Without this, you cannot disentangle the trajectories and just forget. So there is a gap, right? You can see what one big challenge here. It's a little bit nuanced or mathematical, but at least you can intuitively understand that if my initial policy is very unaligned, even if I generate trajectories, it does not make sense to learn a very good reward function on those. So for example, let's say if your objective is to generate text description in Spanish, but your language model is only trained on English, right? So you generate some trajectories or summaries in English and ask the human labeler to rank it in terms of how good it is in Spanish. Does not make sense, right? Yeah. So that's the challenge. So what we do is, so our paper actually is one of the first paper to show some sort of a framework to do that, and shows provable guarantees on that. But that is a big challenge if you can understand that, right? So now what happens is, so now once you have this reward function learned for this policy, you give it again, you learn a policy again, which is a function of r1. Now generate trajectories, human gives preferences, you learn r2, and then eventually it continues till it converges. Now, it might seem that, okay, we can always do it in an online way, right? What is the challenge? The challenge is that when you are designing this, there are some implicit gradient terms that come into the picture, which I will not go into details. I will tell you to read the papers. But are some implicit gradient terms that come into the picture, which we need to deal with, which gives a lot of complexity or brings a lot of complexity into the picture. So now let's just see a visual representation of what we discuss. So let's say this is my agent, and this is my goal that I want to reach, and this is my pi reference. So my reference policy or my initial policy from where I begin. So I generate this trajectory with respect to this goal. But it is important to note that human does not want this kind of trajectories. Human want trajectories which are more towards this, or the human's inherent goal is there, let's say, right? So it's just a representation. So the human's goal is here, and user wants the agent to reach here and not here, right? But it can only answer through preferences. So what eventually happens is it generates just these trajectories, and then the human prefers out of this pairwise trajectories, like we select pairwise trajectories and give to human that which one is better, and accordingly the goal shifts, right? So now the and this goal is kind of reflecting your reward function. So now first the reward function was here, now the goal shifted. Eventually then you collect again feedback and the goal shifts again, and eventually you converge, right? So this is what exactly is RLHF in an online iterative way, which has certain complexities, as I was saying, which is not very straightforward. So let's try to discuss this final pipeline. So what happens, right? So you can see that this is my agent, which is the start point, and this is the goal that it is currently aligned to. But what we need to do is we need to go to this goal, right? That is the humans, or you can say that is basically the alignment objective, or that is my main purpose which I want to reach to. So now what happens is that the the agent wants to reach, so basic, but if you think from a very careful perspective, the agent, while it is running, it just maximizes its own reward, right? It does not know what human wants or what human is willing, right? I cannot like integrate everything at once. So what I need to do is we need to simply learn whatever with the current reward, because in a reinforcement learning pipeline what we need to do is we just have one reward function and the agent can optimize for that. So I cannot do a lot of things with that, but once the reward function is fixed, the agent will optimize for that, right? So now what happens is once this reward function is fixed, the agent optimizes that and it reaches the goal. So for example, in this example when I was showing, so once this reward function or the goal is fixed, it actually learns how to reach that goal. Now what human tells is, okay, this goal is not the most suitable for me, I need something else. So that's why it what happens is it iteratively the goal changes. But once the goal is changed to the next position, it means that the reward function is fixed for that position, right? Now once this reward function is fixed, again the agent will learn how to reach to that goal or to optimize that reward function, and it will generate trajectories accordingly, right? And then eventually the based on this human feedback, the goal shifts and actually it reaches to the final objective. So this is what it is reflecting in this figure. But as I was mentioning that to do it online, there is certain kind of implicit gradients that need to be taken care of. So for example, just to give a very high level intuition of that, not going into too much mathematical aspect of that, is like you have this reward function r naught, from where I learn a policy, and which is pi naught of r naught, and then I generate trajectories, and then I learn a reward function r1. But if you see this reward function r1, it is learned by generating these trajectories, right? Using these trajectories, which is a function of pi naught, which is implicitly a function of r naught. So this reward function is also a function of r naught implicitly, right? You cannot get rid of that implicit dependence. So now when you try to learn this reward function, right, you need to try to take the gradient. We also have to take the gradients with respect to this objective, which is non-trivial, right? And this requires a certain class of optimization, which we discuss in our paper. So this is the very broad objective of and motivation of why is it is needed, what is the purpose of reward design and alignment, and why RLHF was actually doing from a very reinforcement learning perspective. And this is the paper that I like we have done on the, like, very recently it has come up, and it is in archive, and you can all have a look into it. But the objective was the same, that if we have to collect, and this is more like a very general framework, that it need not be pairwise ranking, it can be any sort of ranking, it can be any kind of ranking, or any kind of preferences that human want to give, and it need not be some pairwise preferences, which can be sometimes restrictive, right? So it gives you a more general framework to do that, and it is very much related to how how like in general how any it is also very much related to mechanism design and principal contract design, but these are more econometric or economic terms, so I'll not go into that. But what I want to say is what happens is when you have some goal. So for example, this I told you in the context of RLHF from this chat gpt perspective, but there are different other perspectives. Whenever you are learning a policy, there can be a lot of social aspects to that. So that policy might be socially very hindering, right? That it policy might cause something. For example, chat gpt generates something which is socially not accepted, which is causing bias, which is causing some fairness issues. So in that case, what happens, right? So in that case, how do we align? So that this is the framework of alignment that we basically take. We learn a reward function and we learn a policy which optimizes the reward function, and the reward function is collected using some broader objective or higher level objectives, right? And that is like where this online learning type of framework comes in, that you have an initial reward and then you learn this policy and then you again generate trajectories and see, and eventually when you will at some point you will see that the trajectories have converged and it's like the human are happy with both the trajectories, right? In fact all the trajectories. So when you are in, so basically whenever what kind of whatever summaries you are generating, the human is happy, so you know that it has converged at those points. So this is the broader objective of this paper as well. And these are some, but but there are some open questions, right? That okay, we have got human feedback, but human feedback is very expensive, right? How we can make this framework efficient with less human feedback? And also, like we know that okay, we have got language models which performs exceedingly well. So then the question comes that how uh, like what are the possibilities, or how we can also use some feedback from language model, which is also, I think it's also called RLAIF or something like that. So how can we incorporate also some feedback from language model to do that? And because human feedback is expensive, right? Like you giving preferences to human, like human giving preferences for lot of summaries, you have to go through those summaries and rank, right? So it is still expensive and it takes a lot of cost and money. Everybody cannot do that. So how do we do that? How do we replace humans and take some surrogate of that, which is, but we have to ensure that that's a very important and critical surrogate and an accurate surrogate. Similarly, how do we uh, use language models to do that? And most important question is that what are the theoretical limits of it? What, how do we show that it is provable? So all these questions are kind of unanswered and open questions now, which I think we will be dealing. Yeah, I think that's all from my side. Yeah. That we can discuss the questions.
Yes. Thank you, Shoradip, for taking the things up from the basic
Mm,
stuff so that we
mm.
understand how we have evolved and how we have reached the level at which we have ended the talk on. So thank you
Yes.
so much, and it gives lot of clarity to the community members. While
Mm,
community members have a few questions which also
mm.
aligns to what you have touched upon at some or the other level, and
Yes.
maybe I can repeat those questions a little, and you
Yeah.
can
Sure.
deliver a little bit more
Sure.
insights on that. So as we were talking about the human feedback and
Mm, mm, mm,
all those components.
mm,
So one community member asks, the reward models used in RLHF are
mm,
essential for guiding the models learning. That's the core.
mm,
But how can we reward, like how can the reward models be designed in such a way that they avoid overfitting to the
mm,
to the human feedback that's been provided
mm,
to it? And
mm,
the major goal behind maybe asking this question of the community member might be that how we can avoid the overfitting so that we can end up generating more diverse and
mm.
high quality kind of responses.
Yeah, that's a very good question. Actually, there are several perspectives to overfitting. Okay, but I think the question that is being asked is more from a overfitting to the human preferences perspective. That let's say
Hmm.
there is a language model that has been learned, right?
Hmm.
So which is like PyRef. Now, how do I ensure that by doing this process, how do I ensure that it is not too much far from the pi ref, like it's not like that it has gone very very distant from based on the human feedback, or it has overfitted significantly to the human feedback. So I would say that this is the term, this is the regularization term that helps in that context. So if you think that if this is a minimization objective, right, sorry, it's a maximization objective, so it is like you are kind of regularizing it. So what does it mean is it's saying that okay, this pi theta is something that you are learning or optimizing, so you construct a ball around your pi theta, okay, and you just try to learn within that ball. Once you reach the boundary, you stop, you do not go beyond that, right? So you always project
Yes,
it back to the ball. So what it means is intuitively means that it is kind of preventing it from overfitting.
correct. Yes,
Yeah.
this is helpful.
Yeah.
And there is another question that in the RLHF framework,
Mm-hmm.
like you have worked a little bit more extensively on that, and you might have seen a few things. So what
Mm-hmm.
are the some of the challenges that
Mm-hmm.
comes in effectively combining reinforcement learning with human feedback?
Yes, yes, yes.
Because like we might be very good at doing these two separately, but
Mm-hmm.
what are the various challenges that you foresee when when these both are getting combined, RL with human feedback? So what
Mm-hmm.
are your views on that?
Yes, yes. So I think that is a very good question again. So I think the language model paradigm throughout this entire phase of learning has been very IID. Like we have always learned through IID learning. What does it mean is that the samples are not dependent on each other, although there are tokens. So it's not the correct thing to say that it's an IID learning, because the tokens in RNN and transformers are basically related to each other. But in general, the losses have been like very supervised type of loss, or even in unsupervised, we have made it like auxiliary losses, which are like something of that. But in RL, what happens is there is this Markovian dynamics that we have to say, and this, and what happens is when you integrate that, it becomes unstable. So training this PPO step is not very stable. But OpenAI has a lot of access, and they have the parameters, and because it's a lot of engineering effort once you build this pipeline, there is a lot of strong engineering effort that is needed. So OpenAI has a very solid pipeline to work on that, and they have their own PPO algorithm, which works wonders. So they know how to tune things. But if you do not know, PPO is very unstable. So there are some recent works that we are focusing on. Is there a possibility to do something better and replace like explicit RL step with some implicit RL step, which is
Yes,
more stable? Mhm.
this is helpful. And this comes to one of the follow-up questions that while we are discussing this, and
Mhm.
like while we are trying to see that how the model doesn't end up overfitting and all those stuffs.
Mhm.
So one community member asks a very general question, which
Mhm.
means that they have used ChatGPT quite a some of the times,
Mhm.
and there is still a high chance that the generation of outputs are a little I would say monotonous, or sometimes they're
Mhm.
repetitive, right?
Sure, sure, sure,
So
sure.
they are asking that
Mhm.
one challenge which the community member foresees in the reinforcement learning for language model is the generation of the diverse and creative responses,
Mhm.
which still the people feel that it's not there, but yes, we are improving.
Yes,
So
yes.
their main question is how can we how can the model be incentivized in such a way that they produce more
Mm.
robust and diverse outputs?
Yeah, actually, this is also a very interesting question. So these are all actually, I would say, these are all open questions at this point of time. Research is happening in that way. But interestingly, it is important to understand that. So, okay. So what we need is initially, when if we do not do any sort of alignment, right? Any sort of alignment, what happens is the base language model will do a lot of hallucination. Okay, it will produce some lot of creative things that might be creative, but we do not need creativity everywhere, right? Like for example, I think it is a common phenomenon that you had observed like some several months back, when ChatGPT came. So when we used to say that okay, these are some topics I want, can you list relevant papers, it used to hallucinate and give random paper names, which are creative, because those type of people works on those areas. Okay, but those are not their papers. There are no papers existing like that, and people have spent hours searching for them. So this is just an example, but there can be a lot of other examples which are concerning. So in some sense, that it might not be that creativity is always needed, but for some prompts it is needed. So how do we make it prompt specific, is one thing that need to be learned for sure, is something it's not yet done. And also this overall thing is very much related to this reward design. So that's why I want to emphasize that so human have their own biases, right? I mean it depends on how, from which human I collect the data, right? So they have their own biases, prejudice, because naturally it is there. So in that case, like, so probably, so that in our paper also we focus on that only this pairwise ranking is probably not the best thing to do. We can do something better also. So how do we collect different type of preferences and incorporate them, make it more diversified? So all these questions needs to be thought about to answer this kind of questions.
Yes. And there are like, we will take up last two questions
Mm-hmm.
of today's meetup.
Mm-hmm.
So it's like both of them are related to the sparse rewards and the dense rewards that we touched
Sure.
upon initially.
Mm-hmm.
So one question is, sparse rewards can make learning difficult for RL agents.
Mm-hmm.
Like, can you please help us with certain strategies or techniques
Correct, correct, correct.
to address this issue of sparse
Mhm.
rewards and encourage faster learning?
Exactly. So like I think recently I presented a paper at ICML, which actually talks about how do we do induce exploration, because sparse rewards is like whenever the problem is extremely sparse, the agent will not learn. So we need to have some sort of curiosity or added exploration terms. So if you just search in my profile, you will get different papers like posterior sampling, reinforcement learning, steering is another paper's name, and then heavy tilt policy for sparse reward. So I have been working on this field of sparse reward for quite some time, and what I see is that you can actually, we need to give some sort of exploration, right? We need to give some sort of exploration regularization, right? So one thing is that, so one very naive way of doing that is, let's say when the agent is moving, so let's say the agent has covered some regions, okay? So I tell the agent that if you have covered those regions already, now you cover something that you have already not covered. Okay. So so basically you try to maximize your mutual information. So you try to cover in those region where you have less information, or when you will cover those, you will gain more information. So that is what is called like moving in an information directed way. And that is like one of my recent papers on, which is called steering, is on based on. So you can just go to my Google Scholar and you will get a lot of papers on sparse reward and how to solve them. So these are, so you will see. But that's just
Ye-
the overview is, you add some sort of curiosity term, that okay, I optimize my objective, but let's say I optimize another objective, which is like I maximize my coverage. I need to quickly cover the space. So if I can maximize that also, then I will quickly learn. So yeah, that's the.
Yes, and we will share the profile link of Shauradip's
Hmm. Yeah,
Google research, and definitely we can take the things ahead from there.
yeah,
So
yeah.
the last question which we will be taking up today is, reward design can sometimes introduce unintended side effects or encourage
Hmm.
gaming of the system, right?
Yes.
So, and that's happening immensely in today's world also. So
Hmm.
how can practitioners like us anticipate and mitigate these issues
Hmm.
during our reward design phase in our area of work or in our domain of work?
Yes, very good question. That is a very, very important question. And again, that is one of the motivations of this work that we have written in agent policies with externalities. Because like if you even think that designing reward function, like when we practitioners do that, we tune the reward functions and there is a lot of time that gets spent. So what we can do is we can have some objective and then we can learn, but it is always very important to consider lot of other social objectives, right? And in that case, when we have a social objective, how do we learn the perfect reward function with that social objective, or mitigating like around the social objectives, such that my, so what I want is my policy should also do good. Like basically the agent should be able to reach the goal, but it should not take some path which emits a lot of pollution, right? Or it should avoid some paths which is very risky. right? So this kind of social objectives it should follow. So this actually makes this problem very much inherently bi-level. And there are special classes of optimization algorithms that to solve that we have been doing that in this paper. So I would say that you have a look into this paper, that how with this kind of optimization, if it can solve your objective. And uh, and we are working towards scaling. So this is more like a more theoretical perspective. Now we are working to scale this and to make it in a scale. So maybe eventually those will be helpful to the folks that they're practitioners.
Yes, thank you, Shoradip, for answering that question. And I think most of the questions that come up in this sector are still open-ended questions, because
Mm-hmm.
these are certain areas which are constantly being researched upon, constantly works are
Yes,
happening,
yes.
and it remains exciting domain to be in. And thank you for suggesting this topic and helping the community members learn something new on this topic, while they had suggested something around ChatGPT, but we were not able to think of what what best can the speaker present on this topic. And today, with your topic on reinforcement learning for human feedback, definitely helps the community members around learning this. And
Yeah.
while there are a few questions, but I think more or the less they have been covered. And
Hmm.
I would suggest that I would like we would be posting Shorodip's LinkedIn profile to
Yeah.
the communities group, and definitely people can reach out to him
This is my
in
also
case they
this is
have
my
further
Scholar
questions.
profile,
And we would.
and this just in the chat I have pasted. This is
Okay.
my Google Scholar. Just also paste that, and there are some papers which are on exploration, on dealing with this
Sure.
sparsity.
Sure.
So that will be helpful.
Sure, sure. Thank you, Shoradip, for giving this talk. This is an early morning talk for
Yeah.
you. Thanks for taking the opportunity to help the community members learn. Have a great day ahead. Bye bye.
Yeah.
Thanks to all
Thank
of
you.
you for
Bye.
joining.